Hello everyone and welcome to this module on orthogonal linear coordinate system. We generally have discussed the polar, cylindrical, and spherical coordinate system so far, but today we're going to discuss these coordinate systems in general. However, specifically today we talk about orthogonal curvilinear coordinates. So let's get started by plotting a plane like this. So we have x1 and x2 in here. And we have a curve like this, where we say that we have a vector like r, where it is changed to r plus dr here. So we know that this is, of course, dr, or maybe I can write it here. And we have this as, let's say, ds. So if we talk in limit, so when ds goes to 0, so ds becomes very, very small, where basically dr, the dimension of dr, is equal to ds, then we have this, let's say, e, or this tangent line in here, where a unit vector like this, it can be defined where e, or let me just write this. So if ds goes to 0, so ds becomes so small that the dimension of dr is equal to ds. Therefore, we will have e as dr divided by ds, right? So here you can see that how r is changing with s. So you will have this tangent line or this unit vector here. So in Cartesian coordinate system, if you recall, you had x1 and x2. So if something, if a point, for example, or if a vector actually moved toward the x direction, it was dr. This is our r, for example. So divided by ds here, and this was nothing but dx1. Or if it changed in this direction, in y direction, we had dr with respect to dx2. So ds was the same as x2. But suppose you have a curvilinear coordinate system, like the ones you see in here, like the polar coordinate system. So we had a vector like r, small r here, where you saw that, you have r in here, and you see that it does not change in this direction. So if you just expand or contract it, it does not vary with respect to, for example, theta. It only varies with r. So it becomes like this. ds is the same as dr. But here, if you change, for example, from r to dr in theta direction, you see that you also have this derivative changing, this r actually changing not only with r but also with theta. Therefore, s, let's I don't like to say it like this, but is a function of a length parameter and also angle like theta. But basically, it is not a function, but it is now changed to a parameter which is both length and angle or direction dependent. So for this, we can rewrite S in a form that now it includes, for example, I'm gonna just remove everything in here. So we rewrite this so in curvilinear coordinate system, ds is both length and direction, let's say, dependent. These are only my terms. This might be different, but I just thought that maybe putting it this way would be more easier for you to understand. So they are both length and direction dependent. Therefore, we may state that ds is equal to h d z, something like this, where we have h is, maybe write it other color, this is a length parameter, and we also have here a direction parameter or an angle parameter. All right, so now, for example, when r is changing, you see that it includes h, as well as changing with angle theta, for example. In Cartesian coordinate system, this ds, for example, if it was changing in in x direction. So this is r, and it is changing in this direction. So it becomes r plus dr, something like this. So it was basically 1 dx, or dx1, or it was 1 dx2. So you had the direction, you had the angle, and you also had this 1 as h in here, but we didn't bring it. So basically, it is somehow embedded. This h is embedded in this ds. So in Cartesian coordinate system, this h is 1, but not necessarily 1 for polar coordinate systems, cylindrical, spherical, or any orthogonal curvilinear coordinate. So now let's assume we have like a three-dimensional coordinate system where we have x1, x2, and then x3. And here we have r. This r is a vector we have in here, like r. And now we're going to bring r to define r, not being dependent on x1, x2, and x3, but also on z1, z2, and z3. So instead of writing, for example, ds is equal to 1 dx1, ds is equal to 1, for example, dx2, ds is equal to 1, dx3. I'm going to change this to 3 zeta 2 and then zeta 1. So then r is basically a function of z1, z2, and then z3. And also I can write x as a function of z1, z2, and then z3. Again, x2 can be a function of, can be written in terms of x1, x2, z1, z2, and z3. And x3 can be a function of z1, z2, and then z3. So here, now we need to find this E here, this tangent stiffness. So to do so, I can keep these two constant and vary x1. So I get something like this, for example. And then I keep this and this constant and vary z2. Like I get, this is z1. So I get something like this. This is z2. And I keep these two constant and I vary z3. So I get, for example, something like this. And the collision of these three is basically the point where I have my R in here. So, and I can define E1, for example. I have, this is E2, and I have E3 in here. So now I would like to find this E1, E2, and E3 for this curvilinear coordinate system. So I write E alpha, for example, to distinguish between EI instead of EI. So the partial derivative of R with respect to S, because R is now a function of Z1, Z2, and Z3. So we already said that S is replaced, or maybe write it as ds is equal to h dz. And since here we have alpha, so we will have E alpha, partial derivative of R with respect to H, partial derivative of Z. And here you have Z1, Z2, and Z3. So we have alpha, we put alpha and alpha in here to indicate that this H1, for example, could be different from H2 and from H3. And also Z1 is of course different from Z2 and Z3. Where we have alpha is equal to 1, 2, and 3. And remember, we do not sum on alpha. So we already said that we sum on the dummy indices, but here we do not sum. So I put this in here to make you aware the fact that this is not sum. So basically it is like, let's say it is something like this. And alpha goes from 1 to 3. So now, what is this H alpha? Let's define it. So we have this definition in here. This is very important. And maybe it is a good idea just to say, just to include this. Perfect. So just bring it a bit down. Perfect. All right. So, and let's write an or like this. So what is this H alpha? So basically this H alpha is nothing but the one we have here. So it is basically when we said that if ds goes to 0, so they become very like very close to each other, so they can be assumed lines with the same, so they have 1. The value of H alpha is 1 in the Cartesian coordinate system. Therefore, we use the same terminology here. We have partial R with respect to Z alpha, where we have partial R Z alpha dot product of partial derivative of R with respect to Z alpha, because we know that the length of a vector is its dot product of itself. Perfect. We also have this equation here, which is also very important. Good. We also need some other definitions, like what is the definition of dr? So basically, dr is nothing but the partial derivative of r with respect to z alpha d z alpha. This is the definition that you saw more or less during your undergraduate, graduate, no, even high school for the partial differentiation. And since we have like no sum on alpha, I also put an alpha from 1 to 3 in here. So we have this equation here. And if you recall from here, from this, let's say, let's call it black triangle, from this black triangle, you know that this can be written as, so I just suppress this. So it becomes E alpha, H alpha. So this become sigma alpha from 1 to 3. Just write it this way. All right, so we have H alpha, E alpha, D, Z alpha. And that's it. This is the definition of dr. We also need another definition, which is basically ds squared. So these are all the equations that we need for to proceed further, and also we all derive these kind of equations in the Cartesian coordinate system. So it is nothing but dr times the, let's say, the dot product of dr. So it is equal to, so we have dr already here. So we have sigma alpha from 1 to 3, H alpha, E alpha, D, Z alpha, dot sigma, and this time I use beta. So I have H beta, E beta, D, Z beta. So I can take these two together. So I will have H alpha, D, Z alpha, H beta, D, Z beta, and I have E alpha dot E beta. And since we are talking about an orthogonal, remember this keyword, orthogonal coordinate system. So we have this as delta alpha beta. Therefore, alpha is equal to beta. Therefore, it's become H alpha squared. And then we have D Z alpha squared. And that's it. So this is ds. This is also another important equation here. So next, the only parameter that we need is how this, for example, E1 is changing with respect to Z1, Z2, and Z3. So similar to the polar coordinate system, if you recall. So we had this, let's say, R here. So, and this was theta. We said that okay, so we want to know how ER is basically changing with respect to theta, or how E theta is changing with respect to theta, or R, or whatever. So this is the same concept in here. So we want to know how E alpha is changing with respect to Z. So we want to know So maybe the remaining question is how let's say, how E alpha is changing with respect to Z beta. We want to know how this is changing. The only thing that we know is that we know that it gives another vector. So sorry, it gives another, let's say, a unit vector. So we know so therefore we assume, or let's say, let us define that this will give a somehow unknown unit vector. We use this notation only to show that this is something, as we put a question here, question mark here, so we know that it only has a direction, it has a value in here, but we don't know what is this value. So we're going to find it. This is called the Christoffel symbol. And it might be also a good idea to shift everything a bit, so I can write sigma gamma 1 2 3, because we know that we have like gamma 1 sorry, e1 e2 and e3, so they're different. We do not sum them. So if I write them individually, I will have like gamma is 1, then I have alpha and beta, so I don't have this summation on the dummy index. E1, and this is like 2, alpha, beta, E2 plus, this is 3, alpha, beta, E3. So if we find this Christoffel symbol, so we then will be able to calculate basically the gradient, the divergence, curl, and Laplacian, and so on and so forth. So to find this Christoffel symbol, we have to do some tricks. Now, we would like to find the Christoffel symbol. So, we already mentioned that partial derivative of E alpha, it's here, with respect to Z beta is equal to this Christoffel symbol, gamma, alpha, and beta, E gamma. And be careful, no summation on the dummy indices. So no, so I may forgot to put this no sum on gamma, but you have to be careful about this. So if I change this gamma to sigma, for example, let us replace gamma with sigma sign. So I'm going to have like partial derivative of E alpha with respect to Z beta is equal to sigma, then alpha beta E sigma, and of course no sum on gamma. So sorry, no sum on sigma. And I multiply both by a dot product of E gamma. So next, I have E gamma dot both sides of this equation here. So I'm going to have E gamma dot partial derivative of E alpha with respect to Z beta is equal to E gamma dot sigma alpha beta E sigma. So this will be sigma alpha beta E gamma dot E sigma. And since we are talking about orthogonal coordinate system, so this become delta gamma sigma. So this actually become, so finally I get E gamma E alpha partial derivative of E alpha with respect to CB is equal to, so I can replace sigma with gamma, something like this. This is also another important equation. So now I have this. So I call this like black square. So here, if you remember, we had E alpha is the derivative of R with respect to, is 1 divided by H. Partial times partial derivative of R with respect to Z alpha. So it was, if I remember, yes, black. So from, or maybe I just write it here. So from black rectangular, or substituting black triangle in square gives, so we have ER, right? E gamma. So this E gamma is nothing but 1 divided by H gamma partial derivative of R with respect to Z gamma. And it is basically this equation here. So dot partial derivative with respect to Z beta of E alpha. And now this time I write 1 divided by H alpha partial derivative of R with respect to Z alpha is equal to this, let's say, Christoffel symbol. So I may shift this bit to the right. Then I have the Christoffel symbol in here. So the Christoffel symbol is equal to this in here. Now, if I expand this, so I have 1 divided by H gamma partial derivative of R with respect to Z gamma dot. So I have this in here. So this becomes partial derivative of the first one, H alpha, times partial derivative of R with respect to A. And remember to put all these vectors here. So, you know, I may miss it, but you should know that these are like, this is alpha. These are like vector. So, plus 1 over H alpha. So it is the partial derivative of this with respect to this. So it becomes the second partial derivative of R with respect to Z beta, Z alpha. Perfect. So now we expand it further. 1 divided by H gamma, partial derivative of R with respect to Z gamma times, so if I take this derivative, it becomes 1 minus 1 divided by h alpha squared times partial derivative of h alpha with respect to z beta, partial derivative of r with respect to z alpha plus 1 over h alpha, second partial derivative of r with respect to z beta, then z alpha. Perfect. So I just distribute this over this, so it is 1 over h gamma. So I have gamma and alpha. Okay, so I can write this as minus 1 divided by h gamma, h alpha squared. So I have partial derivative of r with respect to z gamma, partial derivative of r with respect to z alpha, and then I have partial derivative of alpha with respect to z beta plus 1 over h gamma, h alpha, and then I have partial derivative of r with respect to, let's say, z gamma times second partial derivative, and this is dot product basically. So this is dot, of course, and this is dot. No, oh, sorry. This is dot alpha. Let me see. Yes. Okay. So now we have this partial derivative of r with respect to z gamma dot partial derivative of r with respect to z alpha. So let me just write it another color. So you know that this one, this r with respect to z gamma from here, is this portion. So it is equal to E alpha, H alpha. So is E gamma, H gamma dot, or maybe H gamma, E gamma dot, H alpha, E alpha. And basically it is H gamma dot H alpha delta gamma alpha. So we evaluated this based on H, and H, and the only term that we do not know is this. So let me just grab this and make it another color because I'm gonna write this with blue. So we also need to find this out because this is based on R. So we have to write it based on H. To find this expression, we also use another trick. So we already know from here, from, let's say, should call it, let's say, star maybe, I don't know, maybe here, this equation here, star. So partial derivative of r with respect to z gamma dot partial derivative of r with respect to z alpha is equal to h gamma. Sorry, this is not dot, so it is h gamma. So h gamma, h alpha delta gamma alpha. So if I take the derivative of this above equation with respect to z beta, so I'm gonna have something like this. So H gamma, H alpha, and delta gamma alpha. So if I take it, I'm gonna have something like second partial derivative of r with respect to z beta, then z gamma dot. So the derivative of the first one times the second one plus the first one, derivative of r with respect to z gamma dot the derivative of the second one. So this is beta, this is alpha is equal to, all right. So here I take this as one term. So I have the partial derivative of h gamma, h alpha divided by z beta times delta gamma alpha plus the h gamma h alpha derivative of delta gamma alpha with respect to z beta, where we know that this is 0 basically, because it's either 1 or 0. So if we take this derivative, it becomes 0. So for the sake of completeness, let's just write this term as well. Plus h gamma. So you know that I'm taking this derivative, delta gamma alpha with respect to z beta, but we know that this is 0, so it'll become 0. So we have this expression here, and if you know, we have something like, for example, if you have x2 plus y2, for example, and you differentiate this with respect to x first and then y, it is the same as, the differentiation of x squared y squared, this differential equation with respect, so if you take it first with y and then with x, so it doesn't matter, the order of differentiation does not actually affect the solution. Therefore, we would like to let's say cycle over these alpha, beta, and gamma. So since the order of differentiation doesn't affect our final solution, we cycle over alpha, beta, and gamma. So we have alpha, beta, and gamma. So that means if we have alpha, we put beta instead. If you have gamma, you put alpha instead. If you have beta, if you have beta, you put gamma instead. Okay, so let me write this here. So let me see if I can copy this. Copy and paste it here twice. Here. So I do not need this. So maybe this is H and then H. Okay. So I copy and paste this again here. Perfect. Change color. So you have here, just I can zoom out. Okay, I have here beta, so, or just zoom out and copy, paste this in here. Perfect. So I have beta here, and since we have beta, so it becomes gamma. So let me just write it here, alpha, beta, and gamma. So you have gamma here, you have gamma, gamma becomes alpha, you have alpha, alpha becomes beta, you have gamma, gamma becomes alpha, you have beta, beta becomes gamma, you have alpha, alpha becomes beta, and gamma, gamma becomes alpha, and alpha becomes beta. Next, you have gamma, gamma becomes alpha, alpha becomes beta, beta becomes gamma here, alpha becomes beta. You have gamma, gamma becomes alpha, alpha, beta becomes gamma. You have alpha, alpha basically becomes beta, and beta becomes gamma, and you also have gamma, gamma becomes alpha here, and you have alpha, alpha becomes beta, and you have also here alpha becomes beta, and beta becomes gamma. Perfect. All right. So now if I call this is 1. Let's write it with another color. This 1, this is 2, and this is 3. So if I sum 1 and 3 and subtract 2, so I get something like this equation here. So if you pay attention to this 1 plus 3, so just zoom out again. So you see that these two terms, this one and this one, will remain, and this and this, this and this will be removed. Perfect. So this one will remain. So we have the partial derivative of r with respect to z gamma dot. So since this is dot product, so it doesn't matter whether we write the first or the second term. Second partial derivative of r with respect to z alpha, z beta. So we have two of them. So 2 is here. So I put it down here. And I have this term plus this term minus this term. So I have partial derivative of h beta, h gamma. This is with respect to, oh, I forgot to put. So what we have here is beta. Beta becomes gamma. Gamma becomes alpha. So this is, sorry, the first one, h gamma. Sorry, this is h gamma, h gamma, h alpha, and beta, plus this term, h beta, h gamma, z alpha, and we also have a delta, delta gamma alpha, gamma alpha. Plus delta alpha beta, oh sorry, delta beta gamma minus this term partial of h alpha h beta delta alpha beta and then z gamma. All right, so now we evaluated this term, and we also have this term in here. So if I multiply this with this, so h alpha goes with this, and this goes with this, minus 1 divided by h alpha. So again, we assert from gamma alpha beta, the Christoffel symbol, minus 1 divided by h alpha. Then I'm going to have this and then delta. Okay. So this is h alpha with respect to z beta, delta gamma alpha plus, if I'm not mistaken. True. Plus this in here times this value. So it'll become 1 divided by 2 h. So it was h gamma h alpha h alpha times this in here. So let me copy this. One divided by 2h gamma h alpha. Oh, sorry. This will be the Christoffel symbol. This is our solution for the Christoffel symbol. So if I just bring it a bit down, perfect. So, and we can say that this Christoffel symbol for some cases is 0 and for some is not. So we can say if alpha is not equal to beta is not equal to gamma, so if alpha is not equal to beta is not equal to gamma, therefore this gamma alpha beta is 0. Why? Because we have here the let's say the delta operator. So if alpha is not equal to beta, this becomes 0 0 0, and this is also 0. And also it becomes for other situations, like where we have for other cases, like we have alpha and beta, it is also 0. And for also alpha is also 0. You can calculate these yourself. But so for some other cases it is not. So we can say that if you have gamma alpha alpha, it equals minus 1 divided by h gamma, partial derivative of h alpha with respect to z gamma. And also when you have gamma alpha gamma, so you have 1 over h alpha, partial derivative of gamma with respect to z alpha. And remember here, we have no sum. No sum on repeated indices. So with this in mind, we're going to calculate all the possible, let's say the possible partial derivative of E alpha, for example, with respect to Z beta terms. Or for example, if you have, for example, this is gamma, or yeah, beta. So 1 over 1, 1 over 2, 1 over 3, for example, then 2 over 1, and we're going to do this. All right, so let's get it started. We have partial derivative of E1 over with respect to Z1. So we have alpha and beta, and then we have gamma, or maybe it is a better idea just to write it alpha, and this is beta. It's the Christoffel alpha beta, then E dot, and it is, of course, E1. Then we have Z1. So it is gamma 1 1 E gamma. And remember, no summation on repeated indices. Therefore, we will have minus, so we have gamma 1 1. So we come here, gamma alpha alpha. So we have minus 1 divided by h gamma, partial derivative of h alpha, h alpha divided with respect to z gamma. And alpha is nothing but 1, and we have e gamma. So we have minus 1 divided by h1 or maybe it is a better idea to write it the other way around. So we have 1 1 1 e1 plus, so gamma is 2 2 1 e2 plus 3 1 1 e3, which is equal to, so you have 1 1 1 here. So if you have 1 1 1, becomes 0, so this is 0. You have 2 1 1 and 3 1 1, so it becomes this. So you have minus 1 divided by h gamma. H gamma is h2, partial derivative of here h alpha. Alpha is 1, h alpha, yes, and z2 e2 minus 1 over h3, partial derivative of h was h alpha, so it is 1 with respect to z3 e3. All right, so next, change color. So we have partial derivative of e1 with respect to z2. So it is gamma 1 2 e gamma. So it is 1 1 2 e gamma plus 2 1 2, e1, and then we have e2 plus 3, 1, 2, E3. So this is 1, 2, 3. This is 0. This is like this case. And you have 1, 1, 2. So 1, 1, 2. This one is also 0. The remaining is this 1, 2, 1, 2. 2, 1, 2. Like this case. It is 1 divided by h 1 divided by h alpha. It is h1 times this term. Gamma is 2. And then we have z1, e2. Next, we have e1, partial derivative of e1 with respect to z3. So it is gamma 1, 3, e gamma. So it is 1, 1, 3, e1 plus 2, 1, 3, e2 plus 3, 1, 3, e3. So this is 1, 1, 3. So 1, 1, 3 is 0. We have 1, 2, 3, which is 0 because of this case. And the only case is this one. It is 3, 1, 3. 3, 1, 3. It is this one. So basically it is 1 divided by h1. It is 1 divided by h gamma alpha. So it is z1, so it is h3, and this is z1, e3. So let's switch color. We have partial derivative of e2 with respect to z2, which is gamma 2, 2, e gamma. So we have 1, 2, 2, e1 plus 2, 2, 2, e2 plus 3, 2, 2, e3. So we have 1, 2, 2, 1, 2, 2. So it is this one. So it is minus 1 divided by h1, partial derivative of h2 with respect to z1, e1. This is 2, 2, 2. So it is 0. Minus 1 divided by h3, partial derivative of h2, z3, e3. So next we have e2, 2. So e2 with respect to z3, gamma 2, 3, e gamma. So it is 1, 2, 3, e1 plus 2, 2, 3, e2 plus 3, 2, 3, e3. This is 0. This is 2, 2, 3. This is also 0, since we have alpha, alpha, beta is equal to 0. The only case is this one, which is equal to 1 divided by h2, partial derivative of h3 with respect to z2, e3. This is 2, 3. So we have e2, z1. This is gamma 2, 1, e gamma. So it is equal to 1, 2, 1, e1 plus 2, 2, 1, e2 plus 3, 2, 1, e3. This is also 0. This is 0. So finally we have 1 over h squared, partial derivative of h1 with respect to z2, e 1. Next, we have E3 with respect to Z3. We have gamma 3, 3, E gamma. It is 1, 3, 3, E1 plus 2, 3, 3, E2 plus 3, 3, 3, E3, which we know is 0, minus 1 divided by H1, H3, respect to Z1, E1, minus 1 divided by H2, partial derivative of H3 with respect to Z2, E2. Next, we have E3 with respect to Z1, which is gamma 3, 1, E gamma is equal to 1, 3, 1. This is E1 plus 2, 3, 1, E2 plus 3, 3, 1, E3. This is 0. This is also 0. This is equal to 1 divided by H3, partial derivative of H1 with respect to C3, E1. So we have also partial derivative of E3 with respect to C2. So we have gamma 2, 3, 2, E gamma, which is equal to 1, 3, 2, E1 plus 2, 3, 2, E2 plus 3, 3, 2, E3. This is 0, we know it. This is 0. 1 divided by H3, partial derivative of H2 with respect to Z3, E2. This now concludes all the differentiation of these unit vectors with respect to Z1, Z2, and Z3. We may need the second derivative, so we also need to find it out. Second derivative. Because in curl Laplacian, it appears, basically. I'm not quite sure about curl, but in Laplacian it appears. So, all right, so we have partial derivative of E alpha with respect to Z beta is equal to the Christoffel symbol E gamma. So if I take the derivative of this with respect to, let's say, rho, so I'm going to have second partial derivative of E alpha with respect to Z rho and then Z beta is equal to partial derivative of this whole expression with respect to beta, the Christoffel symbol and E gamma. So this is equal to E alpha Z rho partial ZB is equal to partial derivative of Z beta of this Christoffel operator times E gamma plus the Christoffel symbol, and then we have partial derivative of E gamma with respect to Z beta. And if you recall, this here, this gamma alpha beta, this partial derivative of E alpha with respect to Z beta was basically this gamma alpha beta, or the Christoffel operator, partial derivative of E gamma. Who is this? So I can write this expression here as, so using this, we have this to be equal to, so I simply write the first equation here, z beta, then I have gamma alpha beta E gamma plus alpha, gamma alpha beta, and instead of this E gamma E beta, I substitute this gamma alpha beta E alpha. However, I cannot put gamma alpha and beta here, so I have to change this to, so I have to say that this is something like E sigma and this is sigma. So I have gamma and beta here, so I have gamma here, and then I have, sorry, I guess that this is not beta but rho. So let me see. Okay, this is rho, and this is rho. So this is also rho. And I can also rewrite this as sigma, and this is sigma. So finally, I get something like partial derivative of this sigma alpha beta plus gamma alpha beta sigma gamma rho E sigma. Next, since we started from here, where we differentiate with respect to first rho and then beta, so now we swap the differentiation order. We first differentiate with respect to beta and then with respect to rho. So swapping rho and beta doesn't affect our solution as differentiation is order is independent of the order of variables. So we have the second derivative of E alpha with respect to first Z beta and then rho, for example. So we swap these in here. So we have rho of, this become rho. So no, this is beta. This is rho. Yes, and this is also rho. Okay, so we have this, and then we have sigma alpha rho, plus gamma alpha rho. Then we have sigma, so I swap beta with rho and rho with beta. Okay, so I have E sigma in here. So if I subtract, so I had previously 1, 2, and 3. So I have here 4, 5. So if you subtract 5 minus 4, so they should be equal. So they're, if you subtract from them, from each other, they become 0. So what I'm gonna have is basically gamma alpha rho sigma gamma rho minus gamma alpha beta sigma gamma rho plus partial derivative of sigma alpha rho with respect to beta minus partial of this sigma alpha beta is equal to 0. So now if you substitute this with 1, 2, and 3, and you iterate all over them, you get these kind of equations here, which I'm not going into the detail of, of finding them or deriving them. So you're going to have this 1 over h1 3 plus partial z1 1 over h1, this is h3 z1 plus 1 over h2 partial derivative of h3 with respect to z2 and h1 with respect to z2 is equal to 0. And there is also second partial derivative of h1 with respect to z2 z3 is equal to 1 over h2 partial derivative of h1 with respect to z2 h2 with respect to z3 plus 1 divided by h3 h1 z3 and then h3 then z3. So you can find four other terms, four other equations by replacing subscripts 1, 2, and 3. So you have 1, 2, and then 3. So you actually swap them together, like this is strategy that I already used here. So you can use this strategy to find those four terms. So now let's go to to the cylindrical coordinate system to find what are eights here. Cylindrical coordinate system. So in cylindrical coordinate system, if you recall from undergraduate maths, you had r as r cosine theta e1 plus r sine theta e2 plus z e3. So h alpha is basically partial derivative of r with respect to zr, which is equal to, so you have cosine theta e1 plus sine theta. Oh, sorry. Yeah, E1 plus sine theta E2, and then that's it. So this become cosine squared plus sine squared, which is equal to 1. Then you have this is HR, and this is H theta. This is partial derivative of R with respect to Z theta, which is basically minus R sine theta E1 plus R cosine theta E2. So it is R squared sine squared plus R squared cosine squared, which is equal to 1. And you also have Hz, partial derivative of R with respect to Z. So this is equal to E3, so it is 1. So you see, you have HR as 1, H theta as R, and Hz as 1. So you're going to have R theta as minus 1 over HR, partial derivative of H theta with respect to ZR. HR is 1, so this becomes minus 1, and this is also 1. So finally it becomes minus 1. You also have RZZ, which is equal to minus 1 over HR, partial derivative of HZ with respect to ZR, which is equal, this is 0, so this becomes 0. And then finally you have theta, R theta, for example. So this is 1 over HR, which is 1, partial derivative of H theta with respect to ZR, which is 1. So it is 1 times 1, it is 1. So if you move to the spherical coordinate system, so you know that R is nothing but R sine theta cosine psi E1 plus R sine theta sine psi E2 plus R cosine theta E3. So you have HR as partial derivative of R with respect to ZR is sine theta cosine psi E1 plus sine theta sine psi E2 plus cosine theta E3, which is equal to, this is sine squared theta cosine squared psi plus sine squared theta sine squared psi plus cosine squared theta, which is equal to, this is sine squared theta cosine squared psi plus sine squared psi, which is 1, plus cosine squared theta, which is 1. Then we have H theta, partial derivative of R with respect to Z theta. So this is R cosine psi cosine theta E1 plus R sine psi cosine theta E2 minus R sine theta E3, which is equal to, okay, so this is R squared cosine squared psi cosine squared theta plus R squared sine squared psi cosine squared theta plus r squared sine squared theta, which is equal to r squared cosine squared theta cosine squared psi plus sine squared psi. Is that correct? Yes, and plus r squared sine squared. This is 1, and this gives r. Then we have h psi, which is partial derivative of r with respect to z psi. This is minus r sine theta sine psi e1 plus r sine theta cosine psi e2 is equal to r squared sine squared psi plus r squared sine squared cosine squared psi is equal to r squared sine squared. This is sine squared psi plus cosine squared psi. This is 1, and this is basically r sine theta. So now we have h theta, and h psi for this vertical coordinate system. So for example, for the gradient operator, if you recall, the gradient was partial derivative of what we want with respect to xi ei, if you recall. Here it is basically 1 over h alpha, partial derivative of that operator with respect to z alpha e alpha, which actually becomes 1 over h1, partial derivative with respect to z1 e1, plus 1 over h2, partial derivative of what we want with respect to z2 e2, plus 1 over h3, partial derivative with respect to z3 e3. And for example, for divergence, we have the divergence as, if you remember, it was the dot product of del and e alpha. So it was 1 over h beta. So basically it is this one, partial derivative of e alpha with respect to z beta e beta. So basically it is equal to 1 over h beta, and this partial derivative is nothing but the Christoffel operator symbol, sorry, e gamma dot e beta. And this basically is, if you have let's say an orthogonal coordinate system, you have delta gamma beta. So 1 over h beta gamma alpha beta. So sorry, never, for example, gamma is equal to beta. This is 1 over h gamma. We have gamma, alpha, gamma, and this is basically, if you recall from here, so it is gamma, gamma, alpha, gamma, gamma, alpha, gamma. So if you recall from here, gamma, alpha, gamma, it's this one. So this operation here. So you have to put this in here, 1 over h alpha, partial derivative of h gamma with respect to z alpha, which is equal to 1 over h1. Oh, I missed this. 1 over h gamma, sorry, 1 over h gamma h alpha. So it is h1 h alpha, partial derivative h1 z alpha plus 1 over h2 h alpha, partial derivative of h2 z alpha plus 1 over h3 h alpha, partial derivative of h alpha h3 with respect to z alpha. So for example, as a last example, so we're going to do this for the cylindrical coordinate system, so divergence. So in the cylindrical coordinate system, and remember this is E alpha, so it's not a vector. Sorry, it is a vector, but it's just a unit vector. So from here, let's call this 6. So we continue from 6. We have the divergence is equal to, so I write 1 over, I have HR. Instead of H alpha, I put R. So I fill in first with R. So HR, of course, ZR. I'm writing this based on, cylindrical coordinate system, plus 1 over H. This is 2 theta. HR again, since alpha is 1. And we have H theta with respect to Z alpha is, let's say, R again, plus 1 over HZ, HR, HZ with respect to ZR. So plus, we have 1 over HR, H theta, partial derivative of HR with respect to Z theta, plus 1 over H theta, A theta, partial derivative of A theta with respect to ZR, plus 1 over HZ, HR, HZ, sorry, A theta, sorry, this is H theta theta, and this is theta, and this is Z, and this is theta, Z with respect to theta, plus 1 over HR, HZ, partial derivative of HR with respect to Z, plus 1 over Z, Z, H theta, HZ, partial derivative of A theta with respect to Z, Z, plus 1 over HZ, HZ, partial derivative of HZ with respect to Z, Z. So we all know that HZ and HR, they are 1. So for this is 1 and this is 1. So all the derivatives here are 0. These are all 0. So, and we also know that the only term that has a dependency on R here is H theta. So finally it becomes 1 over H theta HR. So this is equal to 1 divided by R. So if we compare this, with the previous solution. So if you remember, we had the divergence of a vector was partial derivative of VR with respect to r plus 1 divided by r, partial derivative of v theta with respect to theta plus VR plus partial derivative of v z with respect to z. And here v is equal to er, which is basically 1 er plus 0 e theta plus 0 e z. Therefore, del er is nothing but this is 1, but this becomes 0. This is 0. This is 0, and this is also 0. So the VR is 1. So finally we get 1.